Imagine this boundary, right?
Yeah.
So extreme that if you cross it, nothing gets out. Nothing. Not even light. It's like the universe's ultimate one-way street. We're talking about black holes, obviously, these huge cosmic mysteries.
Deep mysteries, yes.
And right at the center of it all is this thing, the event horizon. It just seems to defy everything we think we know about, well, reality.
It really does.
So for this deep dive, our mission is simple. Give you the shortcut, get you right up to speed on the event horizon. We've dug through the sources, pulled out the surprising bits, the real aha moments.
Yeah, the stuff that makes you go, wow.
Exactly. Okay, let's unpack this then. What exactly is this cosmic veil?
And it truly is one of the most profound and puzzling areas in all of physics.
Yeah.
The event horizon, it isn't just some theoretical line you draw in space.
Yeah, right.
It's the place where gravity gets absolutely extreme and it crashes right into the weird rules of quantum mechanics. So it challenges, the very foundations of how we think reality works. It forces us to look at these paradoxes that maybe, just maybe, hint at something deeper going on.
Okay, paradoxes are interesting, but let's start with the basics first. Ground ourselves a bit. What actually defines it? Why do people call it the point of no return? That sounds pretty final.
It is pretty final. Basically, the event horizon is the boundary around a black hole where the gravity just becomes overwhelmingly strong.
How strong?
So strong that the escape velocity, the speed you need to actually get away from it, becomes faster than the speed of light.
Faster than light. Okay, that's the universal speed limit, right?
Exactly. And since nothing we know of can go faster than light, well, once you're past that boundary, you're stuck. There's no getting out. It's a concept straight out of Einstein's general relativity.
Which describes gravity as space-time bending, right?
Precisely. Gravity as the curvature of spacetime itself. And for a simple non-rotating black hole, there's actually a formula for this radius. It's called the Schwarzschild radius. The equation is R equals 2gm over c squared.
Okay, wait, g/m/c squared. Break that down.
Right, sorry. G is just Newton's gravitational constant, sort of measures gravity strength. M is the mass of the black hole, how much stuff is in it, and c is the speed of light.
So more mass means a bigger radius.
Yeah, exactly, a bigger event horizon.
Yeah.
And crossing it, well, that means you're inevitably, unstoppably pulled towards the singularity at the center.
The singularity, that sounds intense.
It is. It's a point of theoretically infinite density, all the mass crushed into basically zero volume. Our physics, general relativity included, just breaks down there. We don't have the math to describe it properly.
Infinite density. Wow, okay, that's a chilling thought. So we know what it is and the immediate consequences, well, you're doomed.
Pretty much, yeah.
But let's zoom out. How do these things, these event horizons, actually influence the bigger picture? How do they shape the cosmos? This is where it gets really interesting, right?
Oh, absolutely. On a cosmological scale, the event horizons are really crucial. They're like cosmic architects. They often form when massive stars die and collapse under their own gravity.
Right, supernova remnants.
Sometimes.
Yeah.
Or they could even have formed way back in the very early universe through different processes. And they aren't rare freaks of nature either. They're everywhere.
Everywhere.
Well, we think they're lurking at the center of most big galaxies, including ours, the Milky Way. You've probably heard of Sagittarius A.
Yeah, the supermassive black hole at the center of our galaxy.
That's the one. And these supermassive ones, their event horizons can be enormous, stretching for millions of kilometers.
Millions. Okay, and they just sit there.
Oh, no, not at all. They have a huge impact on how galaxies evolve. They pull in gas and dust, that's called accretion. But they can also launch these incredibly powerful outflows, these jets of particles moving near the speed of light.
Yeah.
Relativistic jets.
Cosmic fire hoses, you mentioned?
Huh? Yeah, that's a good way to think of it. And these jets can actually regulate star formation across the galaxy. Sometimes they trigger new star birth. Other times they blow away the gas clouds needed to make stars. It's a feedback loop.
So they're sculptors, in a way.
Exactly. And something really exciting, we've started to see them in action more directly recently. LIGO and Virgo, the gravitational wave detectors.
Yeah, detecting black holes merging, right?
Precisely. We've detected the ripples in space-time from black holes spiraling into each other, their event horizons colliding and merging to form even bigger black holes. It shows us the universe is dynamic. These things aren't static.
That's incredible. We're actually hearing space-time ripple from these events.
It's amazing. And here's another surprising thing. On the largest scales, they contribute a lot to the universe's total entropy, basically, a measure of disorder. And some physicists even think they might hold clues about dark matter.
Dark matter. How?
Well, it's speculative, But maybe some primordial black holes are the dark matter, or maybe studying them tells us something about it. It hints that there's a whole cosmic inventory beyond just the stars we see.
Wow. Okay, so they're not just passive sinks. They're active, dynamic, maybe even connected to dark matter. Mind blown.
Yeah.
Now, let's get to what you hinted at earlier. Perhaps the weirdest part. This clash between the big picture, Einstein's relativity, and the super small picture, quantum mechanics, right at the event horizon.
Right. This is where physics gets really, really strange.
So what does this collision of theories actually mean for, well, everything?
Okay, so here's a huge aha moment, thanks to Stephen Hawking back in 1974. He realized that if you bring quantum mechanics into the picture, near the event horizon, weird things happen.
Like what?
Quantum fluctuations, basically the inherent uncertainty of empty space, can create pairs of virtual particles, a particle and its antiparticle. They pop into existence for a moment. Usually they just annihilate each other instantly. But right at the edge of the event horizon, it's possible for one particle to fall in while the other escapes.
The other escapes from the black hole's pull.
Just barely, from right near the edge. And that escaping particle carries away energy. We call it Hawking radiation. And the truly mind-bending part, this means the black hole isn't actually black. It glows very faintly, and it loses mass.
It loses mass, so black holes can evaporate.
Over incredibly long timescales, yes, eons and eons. But eventually, they should radiate away completely. They're not eternal prisons, after all.
That completely changes the picture, so they're not perfect vacuum cleaners.
Not quite. And the implication is massive. This radiation seems to be thermal, like heat from a coal. It suggests the horizon isn't this sharp absolute boundary, but maybe more of a fuzzy quantum realm.
Fuzzy?
Yeah, quantum effects blurring that sharp edge defined by relativity. And this directly challenges something called the no-hair theorem.
Wait, back up. No-hair theorem. What's that about? Sounds odd.
Yeah, it's just physicist jargon. It basically says that once something falls into a black hole, all its complex details are lost. The black hole itself can only be described by three simple properties: its mass, its spin or rotation, and its electric charge.
That's it. Like it gets a haircut and loses all its features.
Pretty much. All the information about what fell in seems to vanish, leaving just those three numbers. But Hawking radiation being thermal suggests maybe it's not quite that simple. Maybe some information does get out or is stored differently.
Which leads right into this information paradox I keep hearing mentioned. What's the paradox?
Ah, yes. The big one.
Yeah.
Here's the problem. A fundamental rule of quantum mechanics is that information cannot be destroyed. It can get scrambled, hidden, rearranged, but the universe fundamentally keeps track of it.
Okay, information is conserved.
Right. But if a book or an astronaut falls into a black hole, their information seems to fall into the singularity. And then if the black hole evaporates via Hawking radiation, which seems purely thermal and random, where did the information about the book or the astronaut go?
Does it just disappear, violating quantum rules?
That's the paradox. Does general relativity, black hole eats info, or quantum mechanics, info can't be destroyed, win? Or is there a deeper theory we're missing?
So how are physicists trying to solve this? It sounds impossible.
Well, they're exploring some really wild ideas, trying to develop theories of quantum gravity that can unite these two frameworks. One idea is the firewall.
Firewall, like on a computer.
Sort of, but much more extreme. It suggests that maybe the event horizon isn't a smooth crossing point, but an incredibly high energy barrier that would incinerate anything trying to cross.
Yikes. Okay, what else?
Another really fascinating one is the holographic principle. This suggests that maybe all the information about what falls into the black hole, its entire 3D interior, is somehow encoded onto the 2D surface of the event horizon itself.
Like a hologram, the 3D image stored on a 2D surface.
Exactly. It blurs the line between inside and outside. The information isn't lost, it's just smeared across the horizon.
That is incredibly strange. It messes with your sense of space.
It really does. And then you have broader theories trying to tackle this, like string theory or loop quantum gravity. They suggest maybe there isn't even a singularity at the center.
No singularity. What's there instead?
Maybe something like a fuzzball, a tangled mess of quantum strings, or maybe even a wormhole, a tunnel connected to somewhere else entirely. These are still very much theoretical, very much on the cutting edge. It's where our current understanding hits a wall.
Wow. Fuzzballs and wormholes. It sounds like science fiction, but it's where the actual physics is pointing. What an incredible journey thinking about these extremes. The event horizon really does feel like the ultimate cosmic paradox zone.
It really is. Gravity, quantum physics, information, maybe even the nature of space-time itself, it all converges right there.
So where do we go from here? How do we test these wild ideas?
Well, we're pushing the boundaries. You've seen the pictures from the Eventhorizon telescope, right?
Yeah.
Actually capturing the shadow, the silhouette of the event horizon around M87 in Sagittarius A.
Yeah, those images were amazing, seeing the unseeable.
Exactly. That's direct observation getting closer. And on the theory side, we're using things like quantum computers to try and simulate these extreme environments, to see how quantum effects might play out near a horizon. It's slow progress, but we are inching closer.
It really feels like we're on the cusp of understanding something truly fundamental.
I think so. We're probing the limits of our knowledge.
It really leaves you wondering, doesn't it? Maybe hiding there in the shadow of these black holes are the keys we need to finally unify physics. A reminder, perhaps, that the universe's biggest secrets often lie just beyond the edge of what we can easily see.